This is an important video because it's going to help us learn how to start modeling relationships. We can come up with any idea to test different relationships in the financial markets to see if there's any kind of edge or any kind of insight that we can extract from our data. So to start us off, we're going to build this spreadsheet here. This is just using auto regression. So we're going to be doing linear regression today and building a model, an auto-regressive model, to analyze the same asset we analyzed in the last video, which is XEC USDT. So we're going to perform auto-regression, learn about regression, what is regression, how to estimate parameters that can help us understand the relationship between different variables that we want to use or different data sets that we want to use. And then from there, calculate partial autocorrelation just to tie in nicely with the last session as well, so that everything really clicks together. To start us off, when we think about model building, before we start getting to math notation and numbers and all sorts of crazy funky stuff, let's just start with a graph so we can understand this visually. So I'm going to draw Bitcoin on the x-axis over here and Ethereum on the y-axis. And let's make each axis represent the percentage returns on any given day. So Bitcoin could be anywhere between 1, 2, 3, 4, and so on %. And Ethereum could be the same, 1, 2, 3, 4, and so on %. And let's just mark down some pretend data points over here that we think might resemble Bitcoin and Ethereum for illustration purposes. And you can see that this is starting to really look very positively correlated, i.e. when Bitcoin's returns are high, Ethereum's tend to be high, and when Bitcoins are low, Ethereum's tend to be low. This would signal that these two assets are positively correlated. Now, if I was to ask you to come up with an estimate of Ethereum based on a percentage I give you of Bitcoin, let's say I say Bitcoin is likely going to be at 3% tomorrow. If it is, where would you estimate Ethereum to be? The way you might do that is to draw some kind of trend line. So you might say, okay, I think Ethereum is going to be here at this % return. Now, the interesting thing about this trend line is, number one, you're not far off, right? That makes sense. It makes sense to sort of try to position a trend line evenly in this data and to make some kind of inference based on that trend line. This is a model that you've essentially just built, not just in your mind, but here on this graph. We can improve upon this because we can change the angle of this, the gradient of this trend line. We can move it up or down on this y-axis. In fact, if I leave the trend line where it is right now and assume that this is exactly the perfect position for it for the time being, then when x is at the value 0, we can see, and x being Bitcoin, we can see what value is given to Ethereum. So when Bitcoin is at 0, this is the value of what is known as the intercept. So when Bitcoin is 0, Ethereum will likely be this number here. So this intercept helps us to understand really the height of this trend line. We can position that up or down to help fit things. Now, the next thing you can see here is the angle of the line. So, if we were to draw a trend line and angle it upwards or angle it downwards, the rise over run, you might remember this from math at school, for every tick in data of x across, how much does y change? That's essentially the gradient or the angle. And this, just in math in general, is actually a really important concept. So here is our slope. This gradient we will call our slope. We need some kind of algorithm here that I could manually do that would help me to understand whether I have got this perfectly aligned, as best aligned as possible, a best fit for this trend line. Well, one of the ways I can do it is just look at the distance from my actual data to this trend line. So if I just add up all of these distances, I would come up with an answer. But the problem is these distances can also be negative as well as positive and cancel each other out. So it makes sense to square them. So what we really want to do is sum all of these squared errors, which is also known as the sum of the squares. We want to sum up these squared errors because that'll get rid of all the negatives when we square them. That will give us a number. And if we minimize that distance, that total error, that must mean that we've got our gradient, so our slope of the line, as best as it possibly could be, and also the height of that line, the intercept, as best as it possibly could be. Now, the good news when it comes to calculating the slope is there is a formula for that. And the same for the intercept. We don't have to do this manually, and we don't even have to do it in just 2 dimensions, as we can see later on. We can bring other data points into our analysis too. But let's keep it simple for now. Now, just a slight tangent here. Ordinary least squares is not always applicable. You can't apply it in every scenario, and we'll get more into that later on. There are other estimation techniques such as maximum likelihood estimation. Deep learning, for example, is a technique to estimate parameters, and I do plan to do some very, very in-depth tutorials about deep learning on the Code Raiders channel at some point. But these are all estimation techniques. Right now, I'm showing you how to estimate standard parametric models using ordinary least squares. But just note that it's not always applicable, and you will see as we go through the series when it might not be applicable. Now let's write this down as a formula because we've already spelled it out. Ethereum as of time t is equal to the intercept, which is just a fixed value for any single point in time, plus the slope times Bitcoin at times t, plus some kind of market shock or error to bridge that gap between our estimate and what actually happened. Now we can use some Greek symbols instead of words here because it would get really boring really fast to write intercept and slope out and BTC out, etc. over and over again. So let's just write this as y at times t, which is Ethereum, is equal to the intercept, which we'll call alpha, plus beta times x as of time t, plus we'll use the term epsilon, so this symbol here, epsilon, to represent the error. So we can see now how to make a prediction. If we're making a prediction, we don't know the error yet. So if I'm making a prediction, then I'm going to show that this is a prediction using a caret sign. So we'll call this y at times t with a caret symbol on top. And that is our prediction, which is given by alpha that we will predict. And again, I'm just going to show that with a caret on top so that you can see it's a predicted value, plus beta, which is a predicted value, times x of t. So this little section of our formula here is where we get to make our predictions. And this could be written as y as of time t, could be written as y hat as of time t, plus our error term as of time t. And we could rewrite this to explain what the error term is, which is just going to be the actual versus the predicted value. Now, this error term you will also hear called residuals or our market shock, because the market shock idea comes from this idea that if our model was perfect, there's maybe some random noise that follows a normal distribution that our model won't be able to predict, and therefore this error term will capture that. So one of the tests actually when it comes to linear regression is to see what sort of distribution our error term follows. We're not going to cover that in detail here because it's going to take us off track a bit, but it's just something useful to keep in mind. All right, how do I mathematically estimate this? How do I know what number to use for alpha, which is the intercept, and beta, which is the slope? How do I know what number to use? Well, the formula for slope is just going to be the covariance over the variance of x. So the covariance being xt minus x bar times yt minus y bar, and yt I mean y sub t, and x sub t, over the variance, which we've seen plenty of in prior videos, so I'm not going to harp on about that. But the intercept is then just going to be the average of y minus that slope times the average of x. And there you go. We have our intercept and slope calculations. Now, if we were to bring in more data, which we can do, and increase the amount of dimensions, this is no longer just a 2D plot. We would then have a 3D or a 4D or 5D or an infinite number of dimensions. It just depends how many data points you want to analyze. We could have a model, for example, like this. Y sub t, which is Ethereum at any point in time, is equal to the intercept plus beta sub 1 times x sub t minus 1. In other words, y is just going to be the intercept plus some kind of slope times the prior value of Bitcoin, plus x sub t minus 2, so Bitcoin with 2 lags, plus let's come up with another one, phi or phi, however you want to pronounce it, of y sub t minus 1 plus phi 2 of y sub t minus 2, meaning the last 2 lags of Ethereum itself might also have an impact. Plus maybe even theta, which is just another symbol. I could use any symbols here I want, by the way, and you'll see in different textbooks, different symbols are used. So we could call these pink elephants and orange monkeys if we want to, but just note that each one of these represents a different coefficient. So phi sub 1 is different to phi sub 2. They're not the same thing. They might as well be called A and B. So anyway, we have this theta times the error or market shock in the last period, and then plus some error term to tie it all together. So you can see that you can come up with any idea here and then try to estimate all of these parameters. Now for this multiple linear regression problem here, because we've not just got one coefficient plus the intercept that we're trying to extract out, we've actually got several. We would use multiple linear regression. And in order to do that, you would use matrix multiplication. We won't go through the formulas for matrix multiplication today, but I will show you the Excel function that will just do all of this for you anyhow. So those formulas do exist. They're very easy to get your hands on, and I've used them plenty, but for today's purposes, we won't need them. In future videos, we probably will. So in a moment, you're going to know exactly using Excel how to forecast these parameters. But let's assume you know that already, just taking this a step further quickly. Let's say we now want to forecast this XEC USDT, the returns, and I want to do it based on different lags, so more than just one lag. Well, I can do that now by saying that x sub t is equal to alpha plus beta sub 1 as of x sub t minus 1, so the first lag, plus beta sub 2 times x sub t minus 2, the second lag, and the same for the third lag. And there you go. That would be 3 lags that I'm analyzing. And in fact, if I run 3 simulations of this, or 3 estimates, I should say, of this, one with just 1 lag, one with 2, and then one with 3 separately, I can use those lags to build a picture of what's known as partial autocorrelation. Because really, I would think that this initial, say, beta 1 should look very similar to the autocorrelation figure that we came up with in our previous video. Because if you think about it, this should be some number times the lag should help us to determine the current value, which is essentially looking at the relationship between the current value and the prior value, which is exactly what our autocorrelation function was doing. So this is yet another way to look at that. And if we do it with 3 lags, we can then see how each lag is contributing towards this figure of x sub t. Probably a bit much right now, but we're going to do this in Excel, and then you'll see it graphically on a bar chart, which will help to cement in what's going on. All right, so we've got our XEC USDT. I'm actually not going to call this X right now. I'm just going to call it Y so that you can see it is the dependent variable. And this is our returns data already. It's not the prices. These are the returns. So what I want to do is create the lag, which now I'm just going to call X lag 1. It would have made more sense for me to call this X, but just so you know, this is the dependent variable. It's going to depend on the columns I put here. And so this is X lag 1, which is just going to be that number there. And we can bring that down over here. Now, first of all, what I'm going to do here, and don't worry if you don't have the workbook from the previous session, I'm just going to copy in what the autocorrelation result was for this asset, right? 0.47569, just so you have that from the last video and or in the back of your mind. And then what I'm going to do here is I'm going to calculate, first of all, the slope, which is our beta. Now, you already know the formula for the slope as being the covariance divided by the variance, and you've already done plenty of that calculation in the last 2 videos. So to avoid repeating ourselves with that sort of calculation and adding loads of columns here, I'm just going to put equals SLOPE for slope in Excel, and it'll do all that calculation for us. So our known y's is our column Y here, and then it asks for our known x's, which is this column over here, and I can just hit enter. And there is our slope. Now I'm just going to format this so that all these numbers here are going to be the same sort of format. And you can see these 2 numbers are very, very close. And so they should be, because they're essentially looking at the same relationship. And what about our intercept? So here we want intercept, and that's going to be alpha. And what was the calculation of our intercept? Well, it was the average of y, which is going to be these data points here. And that is going to be minus beta, which is this here, multiplied by the average of x here. Now let's pause here for a second, because there's something really interesting. This slope over here, 0.47663, this is basically saying that any market shocks or errors that happen or residuals that happen are not sustained. They start to decay away because this number is less than 1. So here we can say that this is likely mean reverting. Any shock that happens to this model, in other words, any random event that hits the financial markets that pushes price up, is going to slowly decay away over time. If this was greater than 1, it would mean that those errors persist. And so this is very interesting, and it's very important to understand this because it's going to be quite important when we get to co-integration and testing for co-integration in detail later on. Yes, we are going to get to that. That's an exciting one for me. And this model that we've just built here is known as an AR1 model, an auto-regressive model with a lag of 1. And so we can actually use an Excel formula that should get us the same results as this. It's called linest, which is linear estimator, I guess. And it's going to, again, ask us for the known y's. So I'm going to highlight those. And the known x's. And so I'm going to highlight those here. And it says, do we want a constant? In other words, do we want an intercept? And I'm going to say 1 for yes. And do we want other statistics for making inference and statistical significance tests, etc.? We're going to get to that in another video because I want a dedicated video to testing for the significance of models like this. So here I'm going to put that as 0 for now. And there we go. We have 0.47663, which is exactly this number, and our intercept, which is exactly this number here. So there's our slope, and there's our intercept for this AR1 model. What about doing an AR2? So let's put in 2 lags here, and here we'll create x lag 1, that can be x lag 2, and we'll just make that equals to the same. Then while we're here, we might as well do 3 lags. Why not? Let's just do that quickly. It won't take us long at all. And there we go. Now we've got our lags there. So that's the AR2 formula here. Let's drag this down and across because now I've got 2 dimensions. This is the same as saying x sub t is equal to the intercept plus beta 1 times x sub t minus 1 plus beta 2 times x sub t minus 2. That's what this is saying. Let's just drag that down so that we are looking at like for like over here. And there we go. Now I can see that my first lag here, this is unfortunately, this formula reverses things around. So let me actually just write out here what these all mean, because this can get really confusing really quickly. This here is beta, and this is alpha from a model that just has one variable that it's using as its explanatory variable, or the variable to explain the dependent variable. Okay, so this is just with 1. That's our AR1. Our AR2 is now going to have 2 betas. So this is going to be beta sub 1, and this is going to be beta sub 2. Again, these might as well be called giraffe and elephant. They're 2 totally different things. So you can see here, alpha is now, it's now shifted to the right. Beta has now become beta 1, and it's still looking at lag 1. So I might as well just call this beta 1, so you know it's the same. It's basically the same thing. It's looking at the first lag. Beta 2 is looking at the second lag now, but we want to bring in 3 lags. So I'm going to do that over here. We're going to bring in beta 1, 2, and 3. So let's shift that across there. Shift those over there. And this is now going to be beta 3. Interesting. So we can see here that these numbers change depending on how many data points we're analyzing. And so if I just analyze the last 10, it may not be that useful, and it might actually start detracting away from the accuracy and the quality of the information I'm getting out the model. And of course, there are tests you can do to see, what are the optimum number of lags, for example, to use. And actually, one very useful way of doing that is we can look at this partial autocorrelation function. So a PACF of 0 is going to be 1. And this is very similar to the ACF we did before. So if you didn't watch that video, skip this bit, just ignore it. But otherwise, watch that video because this is going to make a lot of sense. And this here is now going to be PACF of lag 1. And we now know that that's 0.47. A PACF of lag 2 is going to be 0.19. And a PACF of lags 3, I should say, is going to be 0.006. So if we go and bring up a bar chart of this now, this is what it looks like. Here's what my partial autocorrelation function looks like. And it looks a lot like the autocorrelation function chart we did before, except the meaning is slightly different. What this is doing is it's saying how autocorrelated, or how much, I should say, do various lags contribute to the dependent variable I'm trying to predict after the other variables that are in the model have been taken into account. So it's giving you that portion's contribution, or that time step's contribution to the autocorrelation. And we call this the partial autocorrelation function. Let's just go ahead and actually build our forecast, because we haven't done that yet. We've analyzed these coefficients, but we haven't actually built a forecast out of them and looked at what our errors look like. So let's call this y hat, which is our predicted value. And let's do it based on 3 lags, because that's really going to help cement in what's going on. I could say that y at times t, so xec, is based upon this alpha value over here, so the intercept, plus beta 1 times lag 1, plus beta 2 times lag 2, plus beta 3 times lag 3 over here. And that is my forecast for what the returns should be for y. Now we know that these numbers aren't exactly right. In fact, let's format all of this exactly the same so that we can see what's going on here. We can see these numbers don't match exactly, meaning our model's not 100% right, and nor should it be. I'm sure there's many more factors that impact XEC's price than just, its historical prices. However, that said, let's actually see how big the errors are and what they look like. So here we're going to call this residuals. And then here I'm going to say the residuals are equal to the actual minus what we predicted. So this is the error term or epsilon or market shock, whatever you want to call it. And so here we can now say that that prediction plus these residuals are equal to y sub t. And we can now analyze these residuals here to make sure that there aren't things like autocorrelation or issues in the residuals, because these should actually just follow a normal distribution. And so there's all sorts of tests we can do to make sure that we've modeled this at least decently and that these results are at least statistically significant. Now, if anything from this video, really just take away the point about estimation, because this is all about building models that give us parameters that we can learn to estimate. And this is really, in that sense, no different to deep learning. In fact, all of this is about learning relationships and estimating parameters. Whether we're looking at state space models, Kalman filters, or Garch models, or deep learning neural networks, or machine learning algorithms, really it's all about estimating parameters. Now there are caveats to that. If we're doing unsupervised learning, we're not really estimating parameters. We're learning things about our data without defining a model or using models like what we've seen today, these parametric models with coefficients and linear regression equations. The point still stands that you can come up with ideas and you now know how to model them. And in later videos, we're going to get into significance testing as well, so that we can decide whether or not to take these results seriously at all. Regardless, I hope this was a good introduction into ordinary least squares and linear regression, autoregression, and partial autocorrelation. There's a lot we attacked here, so I hope it's starting to click together. Until the next one, take care and talk soon.